Hi apes. Today we're taking a look at Unit 7 Part 2, so we're continuing on with air pollution. So where we left off last time was taking a look at urban air pollution. Now one of the reasons why it might become trapped in an urban area is because of a phenomenon called atmospheric inversion. Now typically what you see in the troposphere is that if we take a look at a temperature profile, and here is cold and here is warm, typically what you see as you go up in altitude is that we are warm at the surface and you get colder. So that is a typical temperature profile. But what happens when you have an atmospheric inversion is actually that you have a little bit of a flip-flop, that you are colder at the surface and then you get warmer and then you get colder again. And what happens is that means that at this layer the air doesn't mix, and so you have this unusual temperature profile that traps air pollution. Now, one of the best ways to show this is with an animation that talks about how this might happen.
Extension. Normally, air temperatures get cooler the higher you go. However, there are times when air at higher elevations is actually warmer than the air below it. This creates what is called a temperature inversion. The atmosphere is mostly heated from the Earth's surface. Sunlight, in the form of short wavelengths of energy, travels through the atmosphere and is absorbed by the Earth's surface. The energy is then emitted back into the atmosphere, but at longer wavelengths of energy. The atmosphere is heated from these longer wavelengths. The farther from the heat source, which is the Earth's surface, the cooler it gets. On calm and clear nights, the Earth's surface can cool very quickly as it loses heat or radiation, cooling the air right above it. At higher elevations, the air doesn't cool as quickly, so this air becomes warmer than the air below it. A temperature inversion occurs when this happens and is called a radiation inversion. Fog may also form if the cooled air is moist. On coasts, a cool ocean breeze can bring cool air onto land. This creates an advection inversion and is very common along much of the California coast. Because the air doesn't mix with other air, pollutants can build up when an advection inversion is present. Sometimes air high in the atmosphere starts to sink. As it sinks, it begins to warm due to the air being squeezed or compressed from the higher air pressure at lower elevations. The sinking air can warm to the point it is warmer than the air below it, even hundreds or thousands of feet above the Earth's surface. Called an upper air inversion, it acts as a barrier to keep thunderstorms from forming. Most inversions last only a few hours, although some may last for days. When this happens, it can cause very poor air quality as pollutants can build up.
So that video does a good job of showing the different ways that this atmospheric inversion layer can form, but the key thing is that what occurs is that you have this unusual temperature profile where rather than our traditional method, if here again we're cold and then we're warm, towards the surface of the Earth we're cooler, aloft we're warmer, and then it gets cold again. And this forms this layer so that any pollution that's formed down here gets trapped in the lower levels of our troposphere. And this picture down here shows what happens when you have this inversion layer that forms, that here's maybe where wind came through and broke up an inversion layer, and here's all that smog that might form with an inversion layer. Now, one of the key components that adds to this pollution within this atmospheric inversion layer is smog. Now we have a couple different types of smog. Photochemical smog is sometimes referred to as LA smog, and this has a yellowish haze to it, whereas our sulfurous smog is sometimes referred to as London type smog. And this has a darker color, so a black or a gray color to it. And so the key difference here is that sulfurous smog comes from sulfur dioxide, so it's sulfur particles that comes from the burning of coal. And it gets caught on the fog, and that's why we often refer to it in the context of London, because London had a real problem with this sulfurous smog prior to the technology that was developed to help to cut down on that sulfur compounds that are released from the burning of coal. Whereas photochemical smog, the key thing here is that you need light. So this requires light to be present. So this is typically only a problem in the summer months for us because you need powerful sunlight. And our key component here are NOx hydrocarbons that are produced from fossil fuel burning, specifically cars. So we're going to go through an animation that talks about how smog forms. So this animation is going to show us here are our precursors. We have our fossil fuels. We have our
Photochemical smog begins when automobile engines, power plants, and factories emit nitric oxide and hydrocarbons. The gases drift into the troposphere. Here, nitric oxide reacts with atmospheric oxygen to form nitrogen dioxide, a yellowish-brown gas. Some nitrogen dioxide reacts with water vapor in the atmosphere to form nitric acid. Exposure to ultraviolet radiation and sunlight converts other nitrogen dioxide molecules to nitric oxide and atomic oxygen. The highly reactive oxygen atom combines with molecular oxygen to form ozone. Both the oxygen atoms and ozone react with hydrocarbons to form aldehydes. In addition, hydrocarbons, oxygen, and nitrogen dioxide react to form peroxyacyl nitrates. Once formed, the pollutants in photochemical smog irritate human eyes and respiratory tracts and damage crops and trees.
Okay, so this was difficult. This is a lot of chemistry that goes on, but our key things to understand are really what goes in and what comes out, so that our precursors are the nitrogen oxide and the hydrocarbons. Now these will go through a series of reactants or reactions, and what occurs, what results, is ozone. And so that's the key thing that I want you to take away from this, is that ozone is the big component of photochemical smog. The aldehydes in the pans, this helps to help that smog stick together. And the ozone is the primary thing that causes the respiratory irritant and the eye irritant for humans. So this is what that secondary pollutant that we're most concerned about. So all of these need to be present in addition to the strong sunlight to make this smog, which is why we often think of it in the context of LA, because they constantly have that sunshine. And they also have a very densely populated area that a lot of people drive. And so you have a lot of cars, a lot of vehicles on the road, so you have a lot of sources of those NOx and hydrocarbons. And then you have that sunlight. So that's why we will continuously have that LA type smog out there. Now this graph up here shows us why ozone doesn't form all day long. So up here in this graph, we have our hydrocarbons and we have our nitrogen oxides that tend to be released in the morning. So they start to build up in our morning, most often because of AM traffic. So in the morning, a lot of people are all going to work at about the same time. And so that is the release of the precursors to it. And then in the powerful sunlight that happens in midday, then that's what allows our ozone to start to form. So this is our ozone curve right here. And so that will start to form once the precursors are in place, and then the addition of that sunlight. So that's why we see that variation of ozone throughout the day. Now, how we can control our air pollution is one way with legislation. We have set the maximum safe limits, and if you are in violation of the NAAQS, we alert the public. We have code red, code orange, code yellow days to alert the public that the air quality might not be good. And there are requirements of industry to reduce the amount of air pollution. So they might be permitted to release a certain amount of pollutants. And we also can do a component of cap and trade where they might be able to set a limit. And what cap and trade does is it makes it economically advantageous for them to reduce their amount of air pollutants so they can trade some of the pollutants that they might have been allowed to create. Now, one thing that we'll take a look at is scrubbers. And what scrubbers will help to do is reduce the amount of SO2 that is released into our atmosphere. So if we take a look at this, a scrubber is something that's done after you burn coal. So here's our furnace and we're burning coal, and you have sulfur dioxide that all comes through here. Now you might have what's called a precipitator that helps to remove ash. And so how we might think of this in our air pollution is it helps to remove our particulate matter. And then it will go into the actual scrubber. And what the scrubber does is it adds a slurry of limestone that will react with the SO2, and it causes it to precipitate out. So it precipitates out that gas. So then what comes out is much less SO2 and much less particulate matter, but you do still have other pollutants such as CO2 coming out. But a scrubber definitely helps to reduce the amount of sulfur dioxide. Now, other things to help with our mobile sources of pollution would be a catalytic converter. So a catalytic converter on a car will help to minimize carbon monoxide, and it takes the carbon monoxide, NOx, and hydrocarbons, and it converts it to something less harmful. Another way that we do this is with a vapor recovery nozzle on gasoline pumps. So you might see this within the hose that helps to prevent those hydrocarbons and VOx from getting released from the gasoline vapors. Now, sometimes you might see it on the hose, and this would be for older cars, but newer cars also have a gas recovery system within them. So they have a way to trap the vapor within the gas tank rather than it escaping. Now, one of the key things to think about, though, is that prevention is always going to be better than cleaning. So the best way to do this is to reduce our fossil fuel use, because most of our air pollutants are coming from fossil fuels. Now, one other type of pollution that's not related to fossil fuels is noise pollution. So noise pollution is a little bit of an unusual one to put in our air pollution, but it is out there. And noise pollution, one of the key sources of that, there's a lot of overlap with transportation, construction, and industry, all the things that make that really loud banging noise. Now, the reason why noise pollution gets attention is because it can really lead to stress and hearing loss in both animals and humans. Now, for animals, sometimes in some cases it will change the migratory or hunting patterns. One big place we see a lot of noise pollution is in the oceans, with seismic testing or with just large ships going through shipping channels. Now, what that can do is it can really change the migratory patterns of our large marine mammals, because they could hear that sound and it can very much stress them out. And then finally, the last type of pollution category in this unit is our light pollution. So light pollution is something you might not always think about, but with light pollution, where you see this is it will, one thing just aesthetically is it helps to prevent being able to really see the stars. So if you're a big stargazer, you might need to go up into the mountains because the light pollution really dilutes our ability to see stars. Another big thing, if you ever go to the Outer Banks, you might see them requesting you to turn off your lights at the in the summer months, because it can affect and it can prevent our baby sea turtles from reaching the sea. Because what the sea turtles will do is, rather than being attracted to the light of the moon, they might be attracted to the light of your house, and they might be going in the wrong direction. Okay, so just two general categories of other pollution to add here. Now we're going to wrap up this unit in the next presentation where we're going to take a look at indoor air pollution as well as acid rain.